everyone. Welcome back from the short break. We will have the second talk of the day today. So it's an honor to introduce Professor Allan H. MacDonald, the Research Foundation Reagents Chair in Physics at the University of Texas at Austin. He is a renowned condensed matter theorist known for his pioneering work on the quantum Hall effect, spintronics, topological bands, different Morie materials like magic angle twisted bilayer graphene, foreshadowing the field of twistronics. He received his PhD from the University of Toronto in 1978. Before joining UT Austin, he held positions at the National Research Council of Canada and Indiana University. He has also held visiting roles at ETA Zurich and the Max Planck Institute in Stuttgart. Professor MacDonald has numerous awards, including the Hertzberg Medal in 1987, the Oliver E. Buckley Prize in 2007, and the 2020 Wolf Prize in Physics. He is a member of both American Academy of Arts and Sciences and the National Academy of Science. So please join me in welcoming Professor MacDonald.
Thank you. I can see that. So for reminding me how old I really am. Can everybody hear me okay? Okay, so I prepared a Blackboard talk. If some of you in the back find that what I write is a little too small to see, there are seats up here up in the front. I plan to give 2 lectures. Both lectures are about Morie materials. And first lecture will be sort of saying, what are Morie materials? How do you build a model of Morie materials? And this platform of Morie materials has, over the last 5-6 years, been an incredibly productive platform for discovering new physics. And in my second lecture, I'm just going to talk about one example, which is a relatively simple example. That's the example of molybdenum ditelluride and similar transition metal dichalcogenide homobilayer Morie materials. Okay? Yeah. So interrupt me at any time, and the ending time of my lectures is prescribed, so I'll get as far as I get. First I want to say something about, well, first of all, one question first. How many of you have actually worked on Morie materials? So maybe about a third of you. So some of this, what I say, will be familiar to many of you, and you can help whenever I get stuck. So first, let me say Morie pattern. So I'm giving a Blackboard lecture. I prepared a Blackboard lecture, and I've been instructed for people online to stick to this part of the whiteboard here, and I hope it'll be enough. A Morie pattern is kind of like an interspatial beating pattern, an interference pattern. And so, for example, let me take an example of a pattern in space. A bunch of lines, like these back lines here, which I guess are off screen for some people. So, I can write this by break it into Fourier components. We know how to do that. So these black lines, actually, their position depend only on x. Yeah, so let me just not normalize it. And so Gn is 2 pi over the distance between lines times n. So that's the Fourier transform of a delta function at all the positions where the black lines are. And let's compare that or interfere that with another pattern in space, which I've drawn over there in red lines, in which I rotate the lines. So G prime is are these sets of wave vectors in the x direction, but rotated slightly. So if I take these wave vectors in the x direction and rotate them by a small twist angle, then the change is in the y direction, and it's proportional to the twist angle. So so there's a correction. These rotated wave vectors are slightly different. And they're in the y direction. And now I can look at the interference pattern between these. Psi prime, let me say, take psi prime star of r times psi of r. And, so this is, now I have these both defined as a sum over Fourier component. So now I have a double sign. Let me use the index, dummy index n prime for the rotated wave vectors. Let me make this a vector notation. Okay, so so this this function is characterized by two sets of reciprocal lattice vectors. If you remember the definition of lattice periodicity, this doesn't have lattice periodicity. But if there's a special set, if G and G prime are similar to each other, for example, the difference between them, that should have been G prime. The difference between them is parameterized by the twist angle theta. Then there's a special set of terms in this sum, in which G prime is just the rotated version of G. Okay, and so that set of terms that vary slowly in space first of all, varies slowly in space in the y direction. I haven't included all the large wave vectors which describe the variations on the length scale of the original pattern A. So this, if I only include these, it's some sort of coarse grain, right? And you can see that this is what people call a Morie pattern. Often, if you look at two similar 2D patterns that are slightly different from each other, and they're overlaid, all you see is the slow spent length scale variations. In here, you can see the distance between the red lines and the blue lines varies periodically as a function of the y coordinate. So what we're going to say is that electrons in the materials we're interested in actually need glasses. They don't see the atomic length scale physics. They only see the Morie scale physics. And you'll see that, we'll see in a minute, in a way very similar to this, that that the effective Hamiltonian is a periodic Hamiltonian, and a 2D electron system that has such an effective, emergent, effective low energy Hamiltonian, that's what I'm calling a Morie material. Okay. So I don't know whether I should, I think I'm going to erase that. And you're all young, so except for the speakers, and so you will remember that perfectly. So okay. Okay, so the example I'm a Morie pattern and of a Morie material is historically the first example. That's 2 layers of graphene. So let me remind you quickly of a single layer of graphene. It has a honeycomb lattice. Let me see if I can draw a honeycomb lattice. Okay, so honeycomb lattice, as you may recall from textbook course in solid state physics, is a non-Bravais lattice. It has a set of points that are on a triangular lattice, and another set of points, separate set of points that are also on a triangular lattice. So if you want to describe all of the if you want to describe all of the points on this honeycomb, you can get it starting from one point by taking a second atom in the unit cell. Here I've called the B sublattice of the honeycomb, and then translating by primitive lattice vectors that I've chosen here to be in the x direction and another one at 60 degrees of the same length. Continuing them by translating these 2 points by all triangular lattice vectors, all integer multiples of, as I've drawn at A1 and A2. Okay, so graphene is a 2-dimensional material that has a honeycomb lattice. There are lots of electrons on every graphene orbital, but near the Fermi level, there's only 1 orbital per carbon atom that is important, and that is the pi orbital, the PZ orbital. If Z is the coordinate perpendicular to the 2D plane. Those orbitals are near the Fermi level because they're the most weakly bound, and so we're only going to keep them. Usually, we only keep them in. That's all that's relevant for the problems we're interested in normally, and so you can build a tight binding model, pi band tight binding model, 1 orbital per site, 2 orbitals per unit cell, and therefore when you build a band model, it's a 2x2 matrix for every wave vector in the Brouin zone, and let me just talk about the simplest case in which electrons hop within the plane only to nearest neighbor sites. Then that means all of the hopping is from one sublattice to the other sublattice. So if I choose my 0 of energy at the on-site energy of this pi orbital, then I'm going to say something. I'm going to write down the Brouin zone here. Okay, so this is triangular lattice Brouin zone. If I choose the real space lattice to have a primitive lattice vector in the x direction, then you may remember that in reciprocal space, one of the reciprocal lattice vectors is in the y direction. And the Brouin zone boundary are the perpendicular dividers of the distance to the reciprocal lattice vectors. So it turns out that there's a special point, and I don't have time to explain this, but it turns out that just by symmetry, the hopping from between the A sublattice and the B sublattice vanishes at the corners of this triangular lattice Brouwen zone. And if I take this tight binding model Hamiltonian and expand it near the corners of the Brouwen zone, then it turns out the expansion coefficient it's linear, and it depends on linear combination kx plus iky, and the coefficient we define in terms of a velocity. So, 1 over h bar d e dk for a block state is the velocity. Let me call this the Dirac velocity of graphene. And this Dirac velocity is speed of light over 300. Okay, so that's typical value actually for velocity of electron in a metal. And yeah. So so if I draw the energy bands along the line that goes from gamma, the center of the Brouwen zone, out to the middles of these spaces, over to K and back to gamma, then as this is so this is gamma M K gamma. Then what will happen? Don't hold me to this, but there's a huge gap from hybridization between these pi orbitals on the two sublattices. Most places in the Brouwen zone, but it vanishes linearly at the K point. So this is the Dirac point of graphene. Okay, and so single layer graphene has extremely simple electronic structure, and the electronic structure of graphene has also active research on it, changes in very systematic ways when you make crystalline systems where you stack layers on top of each other in different ways, like rhombohedral stacking or Bernal stacking. But we're not going to talk about that. We know that in bilayers, for example, electronic structures changes in a very characteristic way. In the bilayer, this band crossing point turns out to be, in simplest description, quadratic rather than linear. But we're interested in what happens when we have a Morie pattern. Okay, so let's take a look at that. So let me try to calculate how the layers couple to each other. And so I'm interested in two copies of this graphene. The one I've put on the bra side of this matrix element is rotated relative to the other. As I said, there are two sublattices for each K. So I want to calculate what these matrix elements are. And we know from a lot of experience with graphite and graphene multilayers of different kinds that the main way in which these generalized graphene multilayer systems, the main way in which the layers influence each other is by electrons tunneling or hopping from layer to layer. They're neutral atoms after all. And so this, we can think of this matrix element that we want to calculate here for the case of two twisted layers. We can sort of guess that's the main thing, okay? So, and I'm going to imagine that, I've written down these wave functions. So the basis functions in the calculation of this matrix element are labeled by a wave vector and by something I've called tau, a label. And that just refers to whether the system is on the A sublattice or the B sublattice, okay? So,
They're all on different layers.
yeah, so this is twist, let's say this one's twisted. That's definitely too small for the back row and not twisted. Okay. So I'm going to make sort of simple approximation here, and I'm thinking of this as, a 2-layer pi band type binding model. And so what I need is, if I normalize each of these wave functions, then I have a bunch of pi orbitals, or I can think of them more modern form as, Wannier functions, so R prime R prime is a lattice vector of the twisted layer. Tau prime is this, vector that from the A sublattice to the B sublattice in the twisted layer. So this is a pseudo block wave function made up of Wannier functions. On the Ket side, I get a similar factor. And then I have some hopping matrix element between Wannier functions, okay? And I'm going to assume that that hopping matrix element, some hopping matrix element that is just a function of the difference between these positions. And let me do it actually, yeah. Okay. So that's reasonable. It's kind of like a 2-center approximation. So we don't know what this function is, but I can always do a Fourier representation of it. And if I want to keep the wave vector of the Fourier expansion of this unknown function discrete, I'll normalize it in this way, and what I have is and E. Okay, does that make sense for everybody? Okay. So now we can sum over all the lattice vectors of both layers. I can sum over all the lattice vectors R prime of the twisted layer. You can see that R prime appears here, and R prime appears here, okay? And so the end result of that sum, as you learn at the beginning of a solid state physics course, is that K prime Q has to equal K prime to within a reciprocal lattice vector. And and similarly, if I sum over all these lattice vectors, K has to equal Q to within a reciprocal lattice vector of the untwisted layer. So I can write this as, and when I do those sums, I get a factor of n. So this is actually, if I 1 over the unit cell area, sum over Q, PQ delta K prime has to equal Q to within a reciprocal lattice vector, whoops, and K also has to equal Q to within a reciprocal lattice vector of the untwisted layer, okay? So that's a double sum over reciprocal lattice vectors, and I should have indicated, yeah, forgot to write that down, okay? I have a double sum over reciprocal lattice vectors, just like the one I erased when I talked about Morie patterns. And yeah, and so you can see that the you know, the difference between K prime and K is you know, is especially small if there's a special set of lattice vectors where the momentum change modulo reciprocal lattice vector is small, and that's where G prime and G prime is just the subset in which G prime is just the rotated version of G. Okay, and that it's those terms that define a periodic Hamiltonian. So let me make a couple of other observations to simplify this. So we're interested in having a model of states close to the Fermi level. That means momenta close to the band crossing point, right? So that means that all of these K's and K primes are close to their Dirac points. And so that means that, you know, that, for example, there's a set here where G and G prime are both 0. That's a special case. And then K prime is equal to K. And Q has to equal both K and K prime, right? And so that means that the value of Q is going to be the wave vector at the Brouin zone corner. Okay. Q is going to vary on the scale of the entire Brouin zone, and all of the Q's that arise in that sum are very close to this Brouin zone corner. So I can approximate TQ by T at the K point of the Brouin zone. Basically, because we're interested in how the wave functions at the corner of the Brouin zone experience interlayer hopping. The fact that they're at the corner of the Brouin zone means that they Fourier transform this function of R at that wave vector. Okay. You know, if you think about what this function of R looks like, I have two crystals. The separation between the crystals in the z direction is much bigger than the lattice constant in play. So if I think about, you know, how this quantity varies on an atomic scale, it has to be smooth, right? Because it's looked at from very far away, which smooths it out. So we know, and you could you know, show this by explicit calculation, that this function TQ is a rapidly declining function of its argument, and therefore we've identified, you know, the smallest Q that can appear near the Brouin zone zone corner. And we only need the most important terms. We know without doing any calculations are the ones where Q is equal to, has a magnitude equal to the magnitude of the wave vector at the Brouin zone corner. Okay. So there's the G equal G prime equals 0 term. It also turns out that if I take this wave vector and translate it by a reciprocal, this wave vector at the corner of the Brouin zone, and translate it by a reciprocal lattice vector, I reach this corner of the Brouin zone. And that wave vector, let me just call it G1, and I'll call this G2. So there are two other terms in which, G is translated from K by either this reciprocal lattice vector or this reciprocal lattice vector. So G is not 0, and G prime is the rotated version of G. But that just gives me the same problem I had here, what goes on at these other two Brouin zone corners is just a rotation by 2 pi over 3. Okay. So let me write down what this model implies, and then we can talk about it. So I'm going to do one other trick here, and or one other step is, if I take this Brouin zone and rotate it a little bit, then the Brouin zone corner point for the K point is moved up in the Y direction, right? If I rotate a layer up by Y, the amount by which it moves in the Y direction, in that case, is magnitude of K times theta. Okay? So K is of order 1 over lattice constant, and this shift of the wave vectors is parametrically smaller by a factor of theta. So this is, this is a small wave vector, just like the small wave vector I showed you when I talked about Morie things more particularly, are in the first point I made. And so I'm just going to change this expression in a convenient way. Okay, so I'm going to shift the wave vector of the rotated layer so that I measure momentum from the shifted Brouin zone corner. And if I pull that all together, what I get is a Hamiltonian, a correction to the original band Hamiltonian. Actually, I'll go by this thing there. So the shift in momentum in going from one layer to the other has this magnitude measured from the Brouin zone corner, and where this TJ's I'll come back to in a moment. So this is a tunneling from one layer to another, and it's sublattice dependent, okay? And the sublattice dependence here in this, in this formula is, we said that Q is equal to K prime up to a reciprocal lattice vector. But we still have a factor then left over of Q, of that, of that reciprocal lattice vector dotted with the difference between these two taus, okay? So these phase factors are remembering where in the original, within the unit cell, in the original layer, at what position was that pi orbital. Yeah. Okay, let me stop there. Any questions? You help me. Okay, so please interrupt at any time, but this quantity here, this TQ has units of energy times area. Here I divide it by unit cell area. So this is just an energy. So in this simple model, the Hamiltonian of the twisted bilayer depends on just one parameter, W. Okay? And when you hop from layer to layer, you can shift your momentum by one of three possible values. These momentum shifts are the one that came from the G equals 0 term, which, is in the Y direction. And so this is, I'll call this Q1. And the contribution that comes from the other two Brouin zone corners it turns out if you go through the details, are these two, okay? So when you hop from layer to layer, measuring momentum in each layer from the Dirac point, there's a momentum boost that you get, okay? So the operator in momentum space is a momentum boost. So in real space, this operator is just e to the minus I qj dot r, okay? So in this approximation, then, we have a sublattice dependent tunneling Hamiltonian that is local. It's just a function of position. When you hop from a certain position in one layer, you hop to the same position in the other layer, okay? Of course, the same means the same compared to the Morie length scale, which has been expanded by a factor of theta. Okay.
If the hopping is sublattice dependent,
Yeah.
Why does it look like the taus completely dropped out?
Where did the taus drop out?
Yeah.
So these factors, thank you for that question, allows me to say that the symbol phi here stands for 2 pi over 3. Okay. And the origin of that 2 pi over 3 was, e to the I, let's say, for example, k prime minus q, which is a reciprocal lattice vector, dot tau minus tau prime. So it's exactly those factors that we dropped when we did the sum over lattice vectors that are giving you these. Okay.
So are we assuming,
Go ahead.
are we assuming that the cat draw are on sublattices or something then?
No, so this is a 2 by 2 matrix. So each momentum boost has its own 2 by 2 matrix.
So there's just implicit.
So this is like, this is AA, BB, AB, BA, etc.
So the tau index is just implicit in the capital T.
Say that again?
So the tau index is just implicit in the capital T.
Yes, exactly. Exactly. Each of the capital T's is a 2 by 2 matrix. So thank you for helping me to recover those details. Anybody else? Okay. So, yeah. Unfortunately, I have to erase that, I think. So, I'm going to, so I want to interpret this formula. So we derive this in a systematic way. Turns out that, you can, this number ends up being, if you put in some reasonable estimates, about 100 millielectron volts. And that's the strength of the coupling between the layers. And it's local in this approximation, just depends on R. So what is this sublattice dependent function of R? What's being captured? So the approximation we made to get this result is the same one when I was talking about Morie patterns. We just only kept, we had, something with a double sum of reciprocal lattice vectors. But we only kept the cases where the reciprocal lattice vector associated with one layer was very close to the reciprocal lattice vector of the other layer, which means that it's just the rotated version of it, rotated by a small twist angle. And so now I'm going to interpret this local function of position. That's the next thing I'm going to do. What is this local function of position give you? Okay. Any questions before I erase this? Okay, so maybe I can erase the left-hand side. Okay. Okay, so T is a 2 by 2 matrix. It's tunneling from one sublattice of one layer to one sublattice of the other layer. And you can see that if R equals 0, this operator in a coordinate representation is just the, this phase factor. But if R is equal to 0, the phase factor is 1. So R equals 0, I rotated two layers that were, took two layers, one right on top of the other, and just rotated. So R equals 0 is actually AA static. In the honeycomb lattices, there's two honeycomb lattices right on top of each other. And what you get when you do the sum all of the diagonal elements of these, if you hop to the same sublattice, you just get one. Okay, and it's only the terms when you hop to a different sublattice, and you can see you get 1 plus e to the I 2 pi over 3, e to the I minus 2 pi over 3. That's 0, right? And so what you get in this model with the two layers at the points in space at R equals 0, and if you go away from R equals 0, you get the same result if for every Morie lattice vector expansion. But let me just say T of R equals 0 for the moment is diagonal. And that's just because you're tunneling to the near neighbor in the other layer. And both honeycomb sites have a near neighbor right above it because the two layers at R equals 0 are right on top of each other. Okay.
Sorry, could you just say explicitly what expression we're calling T of R? Is it just the sum on the right-hand side? So
it's the sum, it's this. It's the sum over these three momentum boost operators, each multiplied by these 2 by 2 matrix. In a coordinate representation, a momentum boost is just a phase factor, right? And so what we're doing is we're summing these three matrices, each multiplied by this function of position. Okay. And that's the result at that position. Then I can take, let me see. Let me take, in order to interpret another position, let me introduce what I'll call the stacking and the relationship between the stacking and the position in the Morie pattern. And so stacking is the difference between the position in the rotated lattice and the unrotated position. Okay, and for small twist angles, that difference, if you recall, is just theta times z cross r. Okay, a vector for clockwise rotation, counterclockwise rotation. A vector that's initially in the y direction, will go now have a small x component, and one that's in the x component will now have a y component, and it will be proportional to the twist angle theta. Okay, so that is d. The meaning of d is how far has locally, as a function of r, has one lattice site moved relative to where it was at zero twist angle. And intuitively, locally, once d has changed by a lattice vector, then the local environment looks the same. And the values of r at which d shifts by a lattice vector, those are the Morie lattice vectors. And so the relationship between r and d, so d is atomic scale. And I can invert this to calculate, for a given stacking, where do I have to go in space to get a given stacking? Okay. And so I can calculate t, this hopping parameter of theta inverse twist angle, z cross tau. Okay. So in other words, I go to a position point in space where the local stacking is such that the A sublattice has locally moved to a B sublattice position. And if you can imagine the honeycomb, that means that the B sublattice has moved to the middle of the hexagon of the layer below. And if you do that, and maybe time's running, so I won't do this, I'll leave this as an exercise. And it turns out that when you put these values of r into these plane wave factors, then q dot r, q is proportional to theta. These values of r are proportional to 1 over theta. So theta drops out, and it turns out that q dot r first one is always 1, and the other ones are at these positions, either e to the I phi or e to the minus I phi. Okay, and so it turns out then that what happens for the diagonal sublattice hopping, you get 1 plus e to the I phi times 1 plus e to the minus I phi times 1. And that gives you 0. So there's no diagonal hopping. And but when I multiply this guy by e to the I phi and this guy by e to the minus I phi, these are all the same. and so I get 3W. Okay. So what it's capturing is that, when I have a given local stacking, the local Hamiltonian changes to reflect the local stacking. And this is the well-known Hamiltonian for the stacking that I get if I translate by tau, which is Bernal stacking, where let's say one of the layers in the top layer honeycomb, one of the sublattice is above a sublattice of the layer below, and the other sublattice is in the middle of the hexagon. And so you only get tunneling to the near neighbor directly above. Okay, so any questions about that? Because I'm going to erase the board. Go ahead.
So you said like this is approximation for small angles. What do you mean by small angles? Is it respective to the lattice?
Yeah, so we used to be modest, but I'm not anymore. So experiment decides what's too much. Should be much less than 5. Should be much less than probably should be much less than 30 degrees. But I think that this it may work. It certainly works very well up to 5 degrees, maybe 10 degrees. Okay, so the upper limit is somewhere at 5, 10 degrees. As you may know, there are certain, when I make this Morie approximation, which gives me a periodic Hamiltonian, I throw away certain effects that actually make some discrete set of twist angles, as you may know, give actual commensurate structures. And those commensurate structures give you extra gaps. So one way to answer your question is how rapidly do those extra gaps go down as you go to smaller twist angles where the nearby commensurate twists are longer period, higher order commensurate ones, and it goes down very, very quickly anyway. You can, one way to answer this question, at least within this two-center approximation, is just to guess how rapidly that function goes down. Okay, good question. Okay, yeah.
I have a question. So the coupling energy W doesn't contain any information about the twist angle?
No, yeah, so this means that in this approximation, this is a model for twisted bilayer graphene at all twist angles. That depends actually on really only this parameter plus the velocity, which is a property of the individual layer. Yeah. Okay, so so the takeaway from that is that the periodic Morie model is really just capturing the dependence of the band Hamiltonian on the local stack. Okay, and I made this argument in terms of that there's some hopping function but there really is no hopping function, but it doesn't matter. Okay? So you can think about this another way, and that is to calculate the following quantity. So this is a recipe for constructing Morie band Hamiltonians. Hamiltonians that have the periodicity of the Morie pattern for any system, okay? And this afternoon we're going to talk about twisted molybdenum ditelluride homobilayers. That's just one example. But for any system, so we've applied this to a bunch of systems. You can apply the approach I'm going to describe right now to twisted bilayer graphene, also to graphene multi-layers, single layer or multi-layer on hexagonal boron nitride, and through all the transition metal dichalcogenide homo bilayers and hetero bilayers, including the group 4 transition metal dichalcogenide semiconductors that haven't been studied experimentally too much yet. So here's the recipe, okay? I'll do this. So, yeah. You know, in all of this Morie stuff, we have 2 layers. Okay? So we're sort of layer. We've been using layer as a label for a state, basis state anyway. And we want to keep that. It's just part, I don't know what happens if we don't keep it. And so we want a Hamiltonian in a representation of layer. So here, L prime L are layer labels. And so, you know, sort of layer, sort of is something in space. So it sort of sounds like we're doing a tight binding model, just like we were for twisted bilayer graphene. So what I really have in mind here is a you know, Wannier function tight binding model, which is you know, you can construct routinely using electronic structure theory methods nowadays. But we're allowing, you know, previously in each layer we just had one orbital, the pi orbital of the carbon atoms. Maybe we'll have many orbitals, okay? Or maybe there'll be just one. But alpha prime is a label. All the relevant orbitals, or I can say all the Wannier functions that I need to build a good Wannier function representation of a Hamiltonian 4-layer alpha. And yeah, so when we write this Hamiltonian, you know, as a function of the local stacking, we're asserting that in the systems of interest, when you move one layer over the other, you can build, you know, you can build a Hamiltonian in the representation of the same set of states. So the Wannier function representation as finite D, and you can imagine, you know, constructing this by just rigidly moving the top layer relative to the bottom. The Wannier functions for orbital alpha should be just translating with the entire layer, okay? And so that works quite well. And so, right. Yeah. So that quantity, which you can routinely get out of the density, you know, DFT calculation, is all you need to build a model. And so I want to take this Hamiltonian, and I'm going to slide over one point here because it's only a few minutes left. And I'm going to take, and I'll maybe come back to the one point if I can. So I can take this Hamiltonian that depends on D and principal and represent its stacking dependence by doing a Fourier transform. So when we do that, we're trying to take advantage of the same property that, the dependence of the Hamiltonian on stacking is smooth on the length scale of the lattice constant in each layer. So these Fourier transforms tend to converge very rapidly, and this function has the periodicity of the lattice. So the expansion is in terms of reciprocal lattice vectors. Okay. So in this Hamiltonian, there's G equals 0 terms. Which don't depend on, it's an average over all stackings, basically. If, for example, a big piece of the Hamiltonian is the isolated layer Hamiltonian, that's independent of stacking. So it's mainly the isolated layer Hamiltonian that emerges when you average over all stackings. And that's some function of K. For example, for graphene, the isolated layer Hamiltonian had these Dirac dispersions. Then I have, sum over G not equal to 0. A bunch of parameters. And in many cases, there aren't so many orbitals that are important. And these terms, because the layers interact with each other, are small, right? And they also depend on K. But if we're only interested in states near some reference K, like the bottom of a band for a semiconductor or a band crossing point in a semi-metal, then all of the Ks are close to some reference K. So for these stacking dependent terms, we can ignore their K dependence, right? Because we're only interested in, these terms are already small. They vary with K on the length scale of the entire Brouin zone, and we're only interested in the small part of the Brouin zone. So mostly, we can ignore the dependence of these terms on K. And okay. And then if I, so we're basically, this is a local stacking approximation. You could imagine, making this the first term in a gradient expansion, where you had terms that are proportional to stacking, proportional to the derivative of stacking. But as long as the Morie periods are much longer than atomic length scale, the local stacking approximation works quite well. And the position, all I need to do to get a position-dependent Hamiltonian is to replace the stacking here by this function of position. Okay. Did I do it? Yeah, that's correct. So R has to vary on the Morie scale in order for D to vary on the atomic scale. And I can write, G dot D that appears in the position dependence here as G dot theta r cross z, which is r dot z cross theta. Okay. So these things, these reciprocal lattice vectors that are smaller than the original reciprocal lattice vectors by a factor of theta, and therefore they describe slow spatial variations and are perpendicular to the original lattice vectors. These are the Morie reciprocal lattice vectors. Okay, so in this way, you can build a model of anything. And so I think I'm running out of time. So I'll stop here, and we'll talk this afternoon about one especially simple application of this, which has a simple looking Hamiltonian, but has really some marvelous properties. So I'll stop here. We have 2 minutes for questions. Or we could just go to lunch. Go ahead.
Just a question from this formalism, can you derive the magic angle for superconductivity in our pattern?
Yeah. So from this formula, this is at the beginning I explained one way to derive the Hamiltonian of twisted the Morie Hamiltonian of twisted bilayer graphene. This is another more general way, and it gives you a slightly more refined Hamiltonian, but it doesn't explain the properties of that Hamiltonian, which give you the magic angle in graphene. So in graphene, it's kind of surprised that because you have an unbounded spectrum, why should strong coupling between the layers give you very, very flat bands? And I'm not going to have time to talk about that today, but we can talk about it offline. For the semiconductor case, I am going to discuss, it's much more obvious why having a long Morie period there's no magic angles. What happens is, because you have classically forbidden regions of energy, then near the band extrema, you get flatter and flatter bands as you make the Morie period longer and longer. Yeah. But other properties of those models were a surprise. Okay. Thank you.
This clock is also fast by about 5 or 6 minutes. So we have some time
okay.
for questions.
Okay. Sorry, I was going by that clock.
Yeah, we should have said. Right over here.
Yeah.
I'd like to, so first of all, thank you for the great talk. I'd like to ask a question about the T matrix. And particularly you mentioned that in the Bernoulli stacking case, I have non-zero HB, okay, B is right top of A.
Yeah.
But then this slanted hopping is 0 in the T matrix that you drew.
Mm-hmm.
Is that coming from the approximation that you approximated T of Q only by T at the K point? Or I want to understand, because from this real space picture, I want to see why this hopping is actually 0.
Yeah. So it's so when we say that it's local tunneling,
right,
it's only local on the Morie scale, right? It's not local on an atomic scale. So there's lots of slanted hopping. That's all included in this formula.
Oh, so you did include the one.
Yeah. So the hop. Let me say it another way. It's related. So the hopping is non-local from layer to layer, right? It's in this two-center approximation, it only depends on how much you move laterally, right? But you're taking this tunneling matrix element in momentum space near the Brouin-Zopf corner. So this quantity, T at K, is the Fourier transform of the position-dependent tunneling. It's dependent on the lattice vector. When the two wave vectors on the bra, it's non-local in space, and the wave functions have a space dependence e to the I k dot r. So it's really the wave functions are taking the Fourier transform of T at the Brouwen-Zone corner wave vector.
I think the question was about whether or not you were including the gamma 3 and gamma 4.
Yeah, and first of all, we're including everything within this approximation. This is within a two-center approximation. So you're referring to gamma 3, gamma 4, blah, blah, right? That refers to a particular type binding model that was historically used to, fit the bands of graphite and fit the bands of graphite, which is a semi-metal, as you know, near the relevant region of momentum space, which is the Brouwen-Zone corner. And that model is actually, sort of not microscopically correct. So there's the topping parameter is more or less a Fourier transform, right? At the Brouwen-Zone corner. And, so these various gamma 3, gamma 4 are fiddling around to get the right dependence on K near the Brouwen-Zone corner. So they don't really have any physical meaning that people often ascribe to. Was that your question?
Yeah, but I think I think I'll formulate in a similar way. And I thought that gamma 3, gamma 4 corresponds to this.
Yeah, so that's what I'm saying. That's all included. Okay, so that's TQ, and Q gets set equal to the Brouwen-Zone corner. That's Fourier transforming whatever this function is, gamma 3, gamma 4 on the atomic scale. And here we've made a separation between the Morie scale and the atomic scale. In practice, the Morie scale is not infinite compared to the atomic scale. It's only 100 times bigger typically, but that's enough. And so when I say it's local in this approximation, it's local on the Morie scale, but it can have any dependence on, second, third neighbor hopping on the atomic scale.
Yeah, another quick question. So in the first way of derivation, in your original paper, there's a zero angle approximation. Basically, you can apply or not.
Yeah.
It basically is whether because the two layers differ by rotation, so each layer Hamiltonian need to be relatively rotated as well.
Yeah.
So in your second way of derivation, is there a way to?
Yeah, no, that doesn't appear.
It's
Yeah.
always zero
Yeah.
angle
Yeah,
approximation.
yeah.
Does the D matrix become spin dependent if you include the spin orbit coupler?
By D you mean stacking? So
Your tunneling.
tunneling matrix, yeah, absolutely. If it's if I think about it this way, this label, this is layer. We privilege layer, right? Because we have to distinguish which is top, which is bottom. But these other orbitals include spin. So it could be spin dependent. And in some cases, it can be. Yeah.
Are there any more questions? If not, let's thank the speaker again.